Okay, so last time we started solving the Schrödinger equation. We have this time-dependent form, I h bar del psi del t is equal to h psi. And inside h is hidden a kinetic energy term, which means two derivatives with respect to the space coordinate, and a potential energy term. So if the potential energy term is time independent, which means there's no time in h, we can do a separation of variables procedure, which says that, well, this psi of x and t can be written in terms of, okay, linear combinations of functions of time times functions of position. Okay, so we can find more than one type of solution in general. And since the equation is a linear one, any linear combination of solutions like this are going to give me solutions to the Schrödinger equation. And we went through some process. We saw that there's this separation constant, and it leads to this t of t, which is going to have e to the minus I e t over h bar. And similarly, for the space part, we have h times u of x is equal to e times u of x. Okay, so h is a differential operator. Operating on u gives e times u. And the terminology is that this e is an eigenvalue. And the u itself is an eigenstate or eigenfunction of the h operator. Okay. Now, it turns out that depending on your problem, excuse me, we have this v of x. Let's assume that it goes to 0 at infinity, may have a certain value, say some negative value in some part of space. And it turns out that if you look for solutions of E with a negative value, what does that mean? The particle is somewhere over here, and it does not have enough energy to go to infinity. Okay, we interpreted this as the energy of the particle. So in that case, I'm going to get a discrete set of states. But if the energy is larger than the value of the potential at infinity, then I have a continuum of values of E. Okay, so for these states, which are now localized to some region where the potential is negative, these things are called the bound states. So they are bound to this region of space. Okay? And they are discrete or quantized. That's where the terminology quantum comes from anyway. Okay? So I have a set of states like that, but if I have, okay, states like this, then they are called the scattering states okay, E corresponds to a continuum. Okay, so these are for E greater than 0, and these are for E less than 0. All right, so we'll return to scattering states later, but for the time being, let's look at the bound states. Okay, so if I have bound states, then I have a certain set of discrete E values. Okay, so I'm going to get H, let me call it UN, is equal to En UN. So I have a bunch of discrete functions which correspond to the eigenstates of our system. Yes?
Also, I couldn't understand well that why the energy levels are discrete.
Okay, well, we'll see as we solve more and more problems that if you want to satisfy the boundary conditions of the wave function as x goes to plus or minus infinity, you have to keep your E at certain values. Otherwise, you are going to get unphysical solutions. You'll get a solution for all values of E. Okay, so you can put in a value of E which is not one of these values, but what happens is you are going to get functions which are not normalizable. Okay, so we will need to keep the values of E at these values so that we get physical functions. Okay, so as we do more and more examples, that will be apparent because that's how you actually find these values. Okay, so those are my bound states. And we looked at the special case. So let me say if, so this is a special case. If my psi at any time, say time equal to 0, is equal to just one of these functions. Okay? So this is called a pure state or stationary state. And we worked out the algebra last time that if you look at any of these expectation values, something like x squared, okay, p squared, and really the h itself is made up of these things. So h and h squared dot dot dot, any really time independent operator, and all of these averages are independent of time. Okay, so that's why we call them stationary states. Okay, the average values do not change as a function of time. Yes?
So by this can we conclude that the average of the momentum is 0? I mean the expectation of momentum is 0?
For a bound state, yes. Okay.
For the pure standing state, I mean.
Well, okay. Why is it 0? It is 0 because the particle is not going anyplace. Okay, so on the average, its momentum is going to be 0. But its p squared is not going to be 0.
No, I'm talking about p.
Okay, p will be 0, yes. Okay, let's then look at, okay, we calculated a few other things. So we looked at the average value of h, and it turned out to be E. And also we looked at the average value of h squared, which turned out to be E squared, which means if I have those things, in fact it's En, right? So that means my uncertainty in total energy is 0. So these states, UNs, are states with definite energies. Okay? There's no uncertainty in the energy of these states. So this is more or less where we left last time, right? Any questions that you want to bring up at this point?
I have a question.
Yes.
When would the expectation value for p squared be 0? Or would
When?
that ever be possible?
Okay. When will it be 0? You see, how did we calculate this value? How did we end up with? Yes. So we ended up with average value of a quantity is equal to something. Then the square of the same thing is equal to the square of this quantity. So that implies that this delta is 0. So we would need to find a wave function whose momentum is equal to something, and then expectation value of the momentum squared is exactly the square of that. Those types of functions, okay, will come up when you have these eigenfunctions. What enabled us to do this? Okay? Just remember, this was un star h un dx, right? Because this is en un, it just gave me this. Now if I have the square here, I am going to get un star h star un dx, which gave me en star, right? Because this is just en squared times un. So I need some type of u which, when operated by the p operator, gives me some p, okay? But p squared, it will give me the square of the value that I have here. Now, those types of things, you can imagine what they are going to be, okay? We are going to study them a lot. Those types of events happen when this function is an eigenfunction of this operator, okay? So we'll then, for those cases, you need eigenfunctions of the momentum operator. But we are getting a little ahead of ourselves, okay? So we'll look at that, yes?
I couldn't understand why the energy takes continuous variables when the particle's outside of the well.
Okay, when the particle is outside of the well, you see, it's all a matter of the boundary conditions. Here, I want the wave function to go to 0 as I go farther away from this well, because the particle doesn't have enough energy to extend all the way to infinity. But over here, the boundary condition is determined by whoever is sending these particles, okay, into this medium. So this is a scattering problem now, and I have my experimentalist here shooting particles, and that person can shoot, okay, use whatever energy he or she wishes. Okay, so in that case, the boundary condition is much more relaxed. All we want is that the particle to have some energy E here. It will do something complicated in this region, but then it will just go on or be reflected, whatever.
Can we say that particle acts classically outside the well, outside of the well, right?
Well, at some point here, the question is will the particle be like a classical particle outside the well? Perhaps not classical, but like a free particle. Okay, a free particle, remember we had this e to the I k x minus omega t type of behavior. So it will just do that. Okay, it will still be a wave. So not technically classical. Other questions? All right, so now let's take everything to one higher state of complication. Let me keep this here, so I'll continue over there. Now, what happens if psi x0 now is not a pure state, but it's a linear combination of these un of x's. So now it's a more general case. Now, you see, this function is usually given to us, and we are asked to find what happens at larger times in t. Okay, so a quantum mechanical problem may be stated as, given this psi x0 equals something, okay, find psi xt, because if I know psi xt, I can evaluate any and all averages that I want. So that's the basic problem in quantum mechanics. Given some initial condition, what happens to the wave function? Okay, so really, whenever you have a differential equation problem as a function of time, this is the type of thing that you encounter. Even in classical mechanics, someone gives you the condition of the system at time equal to 0 and asks you what happens next. Okay, so here, if I have this as an initial condition, now what happens at larger times? Well, I know the forms of the solutions. They must be they must have the form u times t. So in order to satisfy the Schrödinger equation, I must have psi xt is equal to some n Cn un of x, and the time dependence is e to the minus I, that particular energy t over h bar. Okay, so it's simple as that. So all of the difficult, really, all of the difficult part of the problem is solving the differential equation, solving the time-independent Schrödinger equation. So someone gives you a quantum mechanical problem. The first thing you have to do is to solve the time-independent Schrödinger equation and obtain all the ENs and UNs. Once you obtain these UNs and you are given an initial condition, okay, you can then find these expansion coefficients, CNs. That's what I expect you to do in your homework, right? We also last time looked at particle in an infinite well, and what were the eigenfunctions? Okay, sine and pi x over the width of the well. And they are all orthogonal to one another from just simple Fourier series analysis. So you should be able to expand psi x0 in terms of them. So I am still looking at the general problem. I am not, okay, restricting myself to the infinite well, but I'm going to write an orthogonality relation. So un star of x times um of x dx, okay, minus infinity to infinity is equal to delta nm. So no matter what h is, okay, we looked at a certain particular h, which was particle in a box with infinite walls, and we got those sine functions, and they are orthogonal to one another, so they form an orthonormal set of functions with which you can do expansions. But this is true for any un and um. We are going to prove it in the next chapter. So at this stage, okay, the proof is, trust me. Okay, we'll show that. But what that means is now I can go over to this equation, and determine those coefficients using this orthogonality. Okay, so what do? I multiply both sides of the equation by a um star. So if I take psi x0 and multiply it by um star of x dx, okay, in general minus infinity to infinity. I have to do that on the right-hand side also. So I'm going to get summation n Cn, okay, minus infinity to infinity, un of x, um star of x dx. Now I know that this is 0 unless n is equal to m. So I end up with Cm equal to that. So for any given initial condition, I can determine those Cm's. Okay, so let me put this Cm also on the left-hand side and put this thing in a box. Okay, so let's go back to our scenario for solving any general quantum mechanical problem. Someone gives us an H and someone gives us an initial condition. We solve H and determine all these UNs and ENs. That's the difficult part. And then we use the initial condition and the eigenfunctions to determine these expansion coefficients. Once we determine the expansion coefficients, then we just put this back into the equation with the time dependence, and we have the solution to the problem. Okay, so it's that simple, or if you like, that complicated, because it's not always easy to solve the Schrödinger equation. Okay, everything clear? Yes.
How did we find Cn?
How did we find Cm? We evaluate this integral. Okay, so it depends on what the initial condition is. For example, for your homework, I gave you a function which was not one of these UNs. So you know that it's a mixed state, it's not a pure state. And then you multiply that function with all of the eigenfunctions, with U1, U2, U3, etc. Obviously, if you can do it in general, that's easier. And evaluate the integral. And for example, for U5 star dx, you get C5. Okay? Yes?
Might be a silly question, but we're always given with an initial state which has only finite number of UNs, right?
No, it could be infinite. Okay, so this could be an infinite series. It could be one, which is wherever, this case, that case. This is a case when I have just one term in the expansion, but I could have 2, 3, 4, infinite. In fact, if it's a general function, if someone gives me this psi x0 to be some general function like this, okay, without any symmetries or whatever, then in general it's an infinite series. Okay, so you have to, if it cuts off at a finite point, then you are lucky. Okay, so it's a sort of chosen sort of function. Okay, other questions? Okay. Yes.
So we can write any wave function in terms of time independent
Yes.
stationary sign function.
Yes, yes. Okay, so I'm very comfortably saying yes to you, but a mathematician would say, how do you know they are complete? How do you know the expansion is unique, etc., etc.? Trust me, okay? So unless you have a very weird type of Hamiltonian or very weird type of initial condition, these things are all very well behaved. Yes?
We also defined the stationary states as, I mean, they are not oscillating.
Yeah, the averages are not changing with time.
Average is not changing.
Yes.
But they are.
The function itself is changing, of course. So if that's your pure state, let me just go back to this. So if this is psi x0, obviously this implies that psi xt is equal to un of x e to the minus I en t over h bar. Okay, so time dependence is still there. But when you are evaluating these averages, since you have just one term, and since it comes once with a complex conjugate and once as itself, this phase term just disappears. Okay, that's why.
It's standing right up.
No, I don't want to call it a standing wave, but you could, I guess. I mean, okay. Let's discuss this problem again when we get to real standing waves. Okay, standing waves, we usually mean two different solutions moving in two different directions, but you could also call it this. It's just how you name things. Yes?
So for this case, I mean the eigenfunctions case, actually we generally, when I look to it generally says that there is an infinite square well, but what if our function doesn't obey the infinite square well? What we can do, because when we do the Fourier series, it is just apply for the infinite square well. For the
okay, if you have a different problem, then you have a different h and different set of solutions. Okay, so so you must be given a problem. The problem must be defined so that you have a Hamiltonian h, and you find the eigenfunctions, and then you are given an initial condition, and the initial condition is to be expanded in terms of those eigenfunctions. Now, if you change h, obviously it's a different problem.
okay. Because groups generally talks about the basic infinite square wells, so that's why I'm asking.
Yeah, well, infinite square well is the simplest problem to start with. Don't worry, we'll get to more complicated stuff. Okay. Okay. Let's look at the more general case now. So, suppose, given that my initial condition generated a psi of x and t, well, let's start with the zero initial condition first. Okay, so it's going to be, why not? I'll take the general case. So it's going to be some Cn un of x, and then I know that the time dependence must come in as e to the minus I ent over h bar. Okay? So this is now a general form. I must determine psi x0 through this recipe. And once I get it, now I am interested in trying to see what is going on. Okay? Now, let's look at certain points. If this is to be my wave function, I am worried about its normalization. So let's see how this is normalized. So normalization means I integrate this from minus infinity to plus infinity, psi star xt, psi xt, okay, dx. And I'm going to get, okay, two terms like this, minus infinity to infinity, right? Two series, so I have to use different indices. Let me call them n and m. This one will come with complex conjugate terms. So it's going to be Cn star un star of x e to the plus I en over t h bar. This one will come, okay, with index m, Cm um star x e to the minus I emt over h bar. And I have to integrate all of this, okay, with respect to x.
Why do we have un star?
Okay. Be courageous. Just tell me I am doing something wrong, okay? Okay, so that's that. Now, when I look at this integral, you see the only x dependence is over here, unx and umx integrated. So what does that give me?
Summation of Cn squared.
Okay, but okay, Kronecker delta, and we will get only sum over n. Okay, so this integral, along with the integral, gives me delta nm. So it will be a single series. So this will be equal to a sum over n, and wherever I see an m, I'm going to put n again. So it's going to be Cn star, right? And everything is gone. The un's are gone with the integral. And since n is equal to m, the time dependence also vanishes. And I end up with just sum over n of these Cn magnitude squared. So that's nice. My normalization is preserved. Okay, if I normalize it once, it will stay normalized. Yes?
Hocam, for doing this, we need to interchange the integral sign and the summation sign. How can we do that?
If things are convergent, you can change the order, okay? Everything is convergent. So the derivatives and integrals and summations just shuffle around if everything is well behaved under the integrals, okay? Yes?
Did we apply the orthogonality argument?
Yes. That's where this delta nm comes from. Okay, so un, when you integrate over un, you get the delta nm. Yes?
The normalization was conserved.
Because there's no time dependence left.
Okay.
Okay, there's this quantity here is not changing. So if in the beginning I set it equal to 1, it stays 1. Okay. Let's look at something else. Let's look at the average value of h. Okay. So let's then do that. It's going to be minus infinity to infinity psi star xt psi xt dx. So same sort of stuff. An integral from minus infinity to infinity of psi star. So it's going to again be two summations because I have summation over n and summation over m. Yes, thank you. That's why we are starting this journey. We want the expectation value of h. Okay, so now I'm going to get Cn star un of x e to the minus I en t over h bar. And then an h.
It's going to be un star and
Yes,
plus
un
I.
star, thank you, and plus, thank you. And then I have an h Cn, Cm, um of x e to the minus I em t over h bar, this whole thing to be integrated. Okay, so C is just a constant, so H is operating on um, and that gives me em times um, and em is just a constant, so none of those things appear in the integral, but let me write it anyway. Okay, let me group terms, minus infinity to infinity. Okay, so I still have sums over n and m. I have Cn star Cm star. Thank you. Okay, Em. What else? U n star um, and then there is again some term which is not a function of x, but I have to keep it there, e to the I en minus em t over h bar. Integrate over x. So again, the only x piece of the integral is this un um, and that is going to give me a delta nm, right? And I end up with this nice result that says that this is now Cn magnitude squared times En, because I'm setting n equal to m. Okay, so let's see what we obtained here. Let me put that toward the left over here so that I can put a box around it. So this is a summation Cn magnitude squared En, okay, summed over n. So conservation of probability, if I integrate all of the psi's together, I am getting 1. And that is magnitude squareds of these coefficients. Okay? So C1 magnitude squared plus C2 magnitude squared, etc. I add them all up, I end up with 1. Now here I have the average value of E, okay, expectation value of the energy, total energy, which is C1 squared, again, that term there, times E1, C2 squared times E2, etc. So this now gives me an average of the energy. So how can I interpret these Cn's? Yes. Okay, it's the probability, right? It's the probability that the particle is in state 1 with energy E1. It's probability Cn squared with energy E2, and so on. Okay? So that now tells me so now all of this paints a nice consistent picture, because when we looked at the case when we had a stationary state, we had just one state. So we had just C1, okay, or Cn, just one of those coefficients equal to 1. And I had the corresponding energy. Okay? So that means that the particle was definitely in that nth state. And Cn was equal to 1. There was nothing else. All other coefficients were 0. Here I have a mixture coming in from all these bound states. And this says that with probability C1 squared, energy is E1. With probability C2 squared, energy is E2, and so on. Okay? So I would normally write this down, but the board has turned so cluttered that maybe I should.
So, Professor,
Yes.
probability of the function, the probability of function having an energy of n is equal to Cn squared.
Yes. Yes. Okay. So, and that is not changing. Again, an important consequence of this. So, this is as close as you'll get to conservation of energy in quantum mechanics. You have this object which can be in any one of these states with probability Cn squareds, and you get an average energy, expectation value of energy, which is not changing with time. Question? Yes.
Yes. It might be a question for like a later topic, but you don't have to give a very precise
I'll
answer.
decide on it. Yes.
When we take a measurement
Yes.
with a state that is the combination of states, we get one of the ENs when we do the measurement,
Yes.
right?
Yes.
That's the question. Yeah.
Okay. So, but then how do you make the measurement? Okay, you see, whenever this word measurement comes into the picture, okay, it's a little nauseating because,
Yeah.
making a measurement means you are changing the Hamiltonian somehow and things like that. But again, one of the perhaps simplest ways of looking at the energy is just look at the photon that comes out when the particle moves from one energy state to another. So that will give you a signature of what transition happened. Now, even that means that I am looking at a system of an electron and a photon, which we are not discussing here really. So we are sweeping things under the rug to give nice answers, but okay, things are, well, yes.
Does Cn squares, some Cn squares always needs to be 1?
If the wave function is normalized, it has to be, right? Because that's how we.
It could be 1, as I understand. Maybe
I say lots of things. Okay, so a nice normalized wave function always normalizes to 1. Yes.
So we have a nice physical meaning of Cn magnitude squares with the other probability.
Yes.
Is there any like intuitive physical meaning of Cn alone?
Well, not really. It's as meaningful as the psi. So the question is, what is the meaning of Cn? You see, Cn's are building blocks of psi. So it is like asking, what is the meaning of psi itself? So psi by itself, it does not have a very clear meaning. Okay, so Cn's similarly do not have that. Their magnitude squareds are again associated with probability, both for psi and for the Cn's. Okay. Yes.
Hocam, I want to ask about the energy. The
Yes.
ENs. Is there any maximum minimum value of them?
Is there any maximum value?
Yes.
Well, not necessarily.
It can be.
Yeah, if you can supply a particle with that much energy into the system, it can be anything. There's a lower bound to it. It cannot be less than the bottom of your well. Okay, so if you have a quantum well of any shape, you cannot have a particle with an energy lower than the lowest point of the potential energy. It doesn't make sense, right? Then it's okay. The total energy is then less than the potential energy. Yes.
We are talking about the probabilities, uncertainties, etc. But we define potentials like very definitely.
Mm-hmm.
So how is it physical then?
Okay, so the question is, how come we are defining these potentials in a very precise way? Well, if you think about it, that is also a part of, so we keep on asking questions, where does this come from, and where does this come from, etc. So where does this potential come from? Well, most likely, we have the Schrödinger's cat moving around. Okay, he just doesn't know how dangerous quantum mechanics is for cats. Okay, oh, very friendly. Okay, in any case, what we're talking about? Okay, so the potential itself is some sort of interaction of the particle with something else, right? So most likely it is an electromagnetic interaction. Okay, so the type of interactions that we know in nature are things like gravitational interaction, and we cannot solve gravitational quantum mechanical problems because we didn't get the Nobel Prize yet. But apart from that, if you look at the electromagnetic interaction, then we have to put a photon somehow over there. Okay, so the actual problem that we need to solve would be a proton and an electron, and somehow the electromagnetic interaction is mediated by photons, so you have to put those things in. That's called quantum electrodynamics, okay? And it's a very beautiful, precise, etc. So they always brag that they can calculate quantities to 12 significant figures more. So it's a very powerful, nice theory. But apart from that, again, there's the weak interaction and strong interaction and such things. There's always some mediating particles between other particles. Okay, so the answer is that these are now model potentials. These are potentials which are modeling something. So even when we solve the hydrogen atom, for example, we are going to assume a form of the Coulomb potential, which you have seen in your freshman years, okay? Just 1 over r squared type of force, or 1 over r potential, and we are going to use that. But if you want to do things more accurately, we really need to put all the interactions that we know in nature into the problem. So we'll go step by step, okay? So that's the idea. Yes?
We always say that a system state is described by complete set of eigenbases. When they first coming up with this idea, what they were thinking, because we are constructing this as like state is described by this, but in the first place, how did they like think of this? Like,
well, okay, you are asking a historical question. I don't know if I can answer it very accurately. But of course, lots of people were doing very many things. You know the Bohr theory of the atom, which is how these things started. So there were these states which Bohr put around the atom, which were then related to quantization of angular momentum, related to it, but in some inaccurate or even wrong ways. But then, once the mathematical theory was set up, okay, once Schrödinger wrote down the equation, then it's a mathematics, okay, then it's just mathematics. We should also give credit to Heisenberg, who did it in a more difficult way. But the only problems that were solved by Heisenberg's method, as far as I know, are things like harmonic oscillator, and I think some very good mathematicians solved the hydrogen atom or something, but it's not as automatic as Schrödinger's methods. So if you are interested in such things, I recommend that you look at history of quantum mechanics. It is, people were confused in the beginning. Not everyone knew about this. It's mainly something that was developed in Germany. People did not know much about quantum mechanics in other parts of the world. But then as it developed, people learned the methodology. And once you write down the Schrödinger equation, then what I'm telling you here is a nice reduced way of learning it. Obviously, people had to discover this methodology, but that's where you end up if you use the math correctly. Yes?
So we have an initial state, and it evolves according to the Schrödinger equation.
Okay.
But the state will be always a linear combination of the eigenfunctions of the Hamiltonian.
Yes.
So can we say that the state space itself is discrete?
State space? What do you mean by state space?
And all the states constitutes a space, right? Possible states.
Okay. You see, the complete set of states which will describe, or we think, a complete set of states which will describe a system are all of the systems. So let me just put it over here. Remember we said there are these discrete states here and then the continuum. So a general initial condition which may also extend to infinity, you need to include the continuum states also. So the complete set of states mean not only the discrete states here, but also the continuum states. So all of those states, all solutions of the Schrödinger equation form a complete set. Okay.